Hello guys, in this video I'll be talking about the retrosynthesis and we will be solving the complex examples, or we will be doing the practice problem solving for retrosynthesis. I'll be doing examples and you'll be watching how can I do it. And if you are a beginner in retrosynthesis and you have no idea what is it, then please watch my previous videos on this channel in a playlist called retrosynthesis and familiarize yourself with basic terminologies and concepts, and then come back to this video. But if you are an advanced learner, if you are a MPhil student or a PhD student just looking for the examples to do practice, this video is for you guys. Go for it, and just in quick time you can see how many examples we can solve and different strategies, wide variety of reactions that can be employed. Okay, this nucleus is commonly found in cis-jasmone. Now, first thing first, always remember the rule for retrosynthesis. Recognize the functional groups, recognize the relationship. These are the two important points in retrosynthesis, that before you start doing the retrosynthesis, you must recognize the functional groups relationship. And what kind of functional group? Now if you see, this is a ketone and this is alpha position, this is alpha carbon and this is beta carbon, and there's a double bond. So this is alpha beta unsaturated ketone, this is alpha, this is beta, and this is ketone. So you disconnect from this alpha beta unsaturated carbon and you will end up having two carbonyl groups in the one molecule. Now if you count the relationship between these carbonyl groups, there's 1, 2 and 3 and 4. So the relationship between two carbonyl groups is 1, 4, and you can disconnect the bond between 2 and 3 in this way, and the one part becomes the alkyl halide, this one, and one part becomes the control. Why we are adding this extra ester? Because to stabilize this negative charge in the synthesis. This electron withdrawing group ester will stabilize this negative charge, and in this way this can act as a better nucleophile to attack on the electrophile. So how we can do alpha bromination of the ketone? So this is the alpha position and this is also the alpha position, but as you can see this side is blocked. There are no alpha hydrogens, so bromine cannot be added from this side. But there are three hydrogens present on this carbon, which we call alpha hydrogens, and one of the hydrogens is replaced with Br, as you can see here. So this is called alpha bromination of ketones. Now once we have made B, then we can start synthesis from this compound. Now this compound is called active methylene compound, or these hydrogens are called labile hydrogens. Why? Because they contain acidic hydrogens, and this base will act as to deprotonate the acidic protons and generate the negative charge, and that negative charge now can attack on this carbon, and as a result this bromine will leave and you will get this compound. In the next step, we can remove this ester group first by doing hydrolysis to convert ester into carboxylic acid, and then we do decarboxylation, so removal of the carboxylic acid group. Now you have this compound relationship 1, 2, 3 and 4. So the relationship is 1, 4. Now you can connect them by using intramolecular aldol condensation reaction, and the target molecule is 190. That's it. So this is how we can do the retrosynthesis of these complex molecules. Okay, let's have a look at the next example. Now, if you look closely to this example, there are alcohols. 2 alcohols are primary and 1 alcohol is secondary. What you can do is FGI, convert all of the alcohols into their corresponding functional group. So this primary alcohol is converted into ester by doing FGI, and this alcohol is also converted into FGI by ester, and this alcohol is converted into ketone. But when you will do a reduction of this ketone, you will get back this alcohol. When you will do reduction of this ester, you will get the alcohol, as well as when you reduce this ester, you will get the alcohol. That is the forward direction. But in retrosynthesis, we go by backward direction. Now, once you do FGI, now you can see there's some relationship between the carbonyl compounds. So as you can see the numbering in the black, so relationship between 2 esters is 1,5, while the relationship between 1 ester and 1 ketone is 1,4. That's what I'm talking about. So this is the carbon 1. We arbitrarily do numbering. So this is 1 and this is 5. So the relationship between these 2 esters is 1,5, but the relationship between this ester and this ketone is 1,4. Now we can disconnect this bond between 2 and 3, as well as from 3 and 4, because 1, 2 and 3 and 4. So in this direction there's a 1,4 relationship, and also in this direction there's 1,4 relationship. So that's the 1,4 dicarbonyl group disconnection, and we disconnect the esters from 2 position and 4 bond between 2 and 3 and bond between 3 and 4, and you will get the simple ketone. This is the simple ketone. Now you have 2BrCH2CO 2ET. If you start your synthesis from this compound, this is sodium hydride, which will act as a base. Now this base will deprotonate this proton and generate the negative charge there. Now this negative charge will attack on this carbon, and this bromine will leave, and you will get this compound. Because there are 2 hydrogens there, you can take both of the hydrogens and replace both with the esters. And in the last step, you can use lithium aluminum hydride to reduce the ester as well as the ketone group. So lithium aluminum hydride is a powerful reducing agent that will reduce this ketone into alcohol, as well as it will reduce this ester into alcohol, as well as it will reduce this ester into alcohol, and you will get the target molecule 192. Okay, let's move on to the next example. If you look at this example, there's a 1,6 relationship between these 2 carbonyls. So what we do is reconnect and connect them to make 6-member ring. For example, if you count the relationship here, 1, 2, 3, 4 and 5. Okay, we can do reconnection as well. We can write this compound as this way, and if we do this, there is a reconnection, and this is the compound. Now do FGI, convert alkene into alcohol, and then delete the phenyl ring and make the Kegnard reagent and the cyclohexanone. Now the synthesis is very interesting. In this case, we have to do the ring opening reaction. So first we react this with the phenyl bromide which will react with magnesium, and then it will react with Et2O and then cyclohexanone. First, this cyclohexanone will be converted into alcohol, and with H3PO4 this will be dehydrated. This is a dehydrating agent, phosphoric acid. It will dehydrate this alcohol and we will have the alkene here. That's one. And in the last step, we can use ozone lysis in the peroxide workup to give you the carboxylic acid. Why we are using this peroxide workup? This oxidative workup that will oxidize the aldehyde into the carboxylic acid. It will not stop at the aldehydic stage, hence it will go to the final oxidation step, that is the carboxylic acid. Have a look at this structure. Now count the relationship to 1, 2, 3, 4, 5, 6. So the relationship between the two carboxylic acid groups is 1, 6. We do the retrosynthesis by using the reconnect approach. We cyclize this into this compound, and in the next step we do Diels-Alder reaction. So this is the diene to alkenes, and this is the dienophile. So they react together to give you this. So first they react with this to give you this one in a Diels-Alder reaction, then do ozonolysis to give you this, and then in the last step you ring opening of this cyclic ester to give you the target molecule. The next compound, the next approach is this Birch reduction reaction. This is a toluene reacting with sodium in liquid ammonia to give you this compound 1, 2, 3, 4, 1, 4 diene. Now if you look at this compound, it's containing alkene, ester, alcohol. So 3 functional groups are present there. What we first do is FGI, convert this primary alcohol into aldehyde, and then do reconnect strategy. So if you count the relationship between this aldehyde and ester, it's 1, 6. 1, 2, 3, 4, 5, and 6. You reconnect it and you will get this compound, and then you do the Birch reduction to reduce this compound into this compound. In the synthesis part, you can do Birch reduction first to reduce the double bond, and in the next step you do the ozonolysis of both of these double bonds. So cut from this position and cut from this position. So this cut first one will give you this ester and then the aldehyde. So in ozonolysis, the first the bond breakage will be from the position where we have the electron donating group. So first this bond will be broken, not this one, because methyl group is less electron donating compared to the methoxy group. Hence the ring opening will take place from the methoxy carbon, not the methyl carbon. And in the last step you will do the reduction to reduce this aldehyde with sodium borohydride and keep this ester to get you the target molecule. If you use here strong reducing agent, powerful reducing agent such as lithium aluminum hydride, what you will do, you will end up by reducing this ester as well as aldehyde. In order to avoid this situation, we have to make sure you protect the chemoselective approach. We first reduce this aldehyde, and then in this way we can protect this ester group, right? So with a mild reducing agent such as sodium borohydride, it can be only used to oxidize the aldehyde. let's look at the next example. So this is the next example. If you recognized functional groups, it's the alpha beta unsaturated carbonyl compounds. That is the aldehyde and this unsaturated alkene. So first you disconnect from this double bond position, and you get this ketone on one side and aldehyde on the other side, and you do the reconnect strategy of 1,6 dicarbonyl groups, and you get this compound, and then you do the retrosynthesis retro-Diels-Alder reaction to give you these two fragments. When you will do synthesis, you first combine these two to give you the reagent A, and then you do epoxidation with any peroxy acid like MCPBA, metachloroperbenzoic acid, that will give you the epoxide, and then you will react with the water in acidic medium to ring opening of this epoxide to give you the diols, and in the next step you will react with sodium periodate to do oxidative cleavage of this diols. One dialcohol will give you the aldehyde and another will give you the ketone, and in the last step you react with piperidine as a base in acetic acid. Then the cyclization reaction will take place and the ring contraction will take place, and it will give you the target molecule. Next molecule is this one. So this is the molecule which also has multiple functional groups, like two functional groups. One is cyclic ester and alcohol, and then you first disconnect from this position, and one side becomes alcohol and another side becomes carboxylic acid and OH, and then you disconnect this position, so 1 and 2 bond. So these are the two different functional groups, 1, 2 difunctionalized compounds. You disconnect from this carbon, and then you will get this fragment as well as this fragment. Again, you have a couple of functional groups here, 1, 2 and 3. So you have a 1,3 dioxygen containing functional groups, or you can oxidize this alcohol into aldehyde and disconnect it from the 2 and 3 position. Now the synthesis part is starting from this aldehyde, react it with formaldehyde in potassium carbonate as a mild base. The aldol condensation reaction will take place. You will give this product, and then react this aldehyde with KCN. The hydrocyanine formation will take place. So cyanide and hydroxyl group will take place at the 1 carbon, and you react it with HCl to do the hydrolysis of this cyanide, and followed by the cyclization to give you the target molecule, this one. That's how you do the retrosynthesis and synthesis of this compound. So next is this molecule. As you can see, there's a ester group in it, and first we will do disconnection from the ester position, where it will react it with the ring opening reaction will take place, and so when the ring opening takes place, then do FGI to give you the alcohol and the carboxylic acid on the other side, and then you do the FGI, you convert OH into the ketone and acid. Then you count the relationship between the two carbonyls, 1 and 2 and 3 and 4 and 5. So there's a 1,5 dicarbonyl relationship between these two carbonyl groups, that is the disconnecting from the position 2 and 3 to give you this compound, and then this compound. And if you do the synthesis, you first react this compound with sodium hydride and formalate ester to get the negative charge at this position and do the nucleophilic part on this carbonyl group. You will get this. We are writing this whole part as AR. Then you will react it with the bulky base, potassium terbutoxide. A negative charge will be generated here, and then this will react with the Michael acceptor on the double bond, and you will get this compound with mild reduction. Only ketone group will be oxidized into alcohol. And in the second last step, we do the hydrolysis in the basic media to convert these esters into the carboxylic acids, and one of the carboxylic acid then it will react with alcohol to give you the cyclized product. And after the heating, the extra acid group is removed to get you the target molecule. So one thing that might confuse you guys, that we have written this whole part, this one is AR. This is equals to AR, because instead of, sometimes in most of the organic compounds, these are the simple, to simplify the things, we use the abbreviated terms like AR for the whole part. It doesn't mean that we are not considering that part, but we are just not highlighting it. Why? Because it is not that much important in it, okay? And then it's less important than this one. That's why we are writing it as the AR. And if you go on, and let's have a look at the next example, which is this one. Again, it's a cyclic ester, so we disconnect from this position. Ring opening will take place. One part will become ester and one part will become the alcohol, and then the next part will be this one, do FGI to convert this OH into the ketone, and the one part is ester. Then we do reconnection 1,6 to get this T-Lalder or add activating group, and then do 1,4 dicarbonyl disconnection to give you this, or you can do route this way, 1,5 dicarbonyl to get you this, or you can do 1,5 dicarbonyl this way, and then 1,3 and 1,3. The synthetic route is for that compound is this one. Here's the synthetic route. So this is the starting material. You react with sodium hydride and then react with diester to give you this compound, and then you react this compound with this reagent to generate this. Then do the hydrolysis of the esters to give you this couple of esters. Then you reduce these esters into alcohols and do cyclization in the presence of acetic acid to give you the target molecule. I hope you like this video of practice problems, very complex problems of retrosynthesis in this video. But if you have any confusion, doubts, please drop your comments below in this video. I'll try to explain them, and I'll be making more videos about retrosynthesis. And I forgot to mention that I am following the Stuart Warren workbook for this video. I'm taking examples from the Stuart Warren workbook. Thanks for watching. Take care. Bye.